Conference. My name is Carsten Kruse from Saarland University. And before we start, I would like to remind you that this afternoon session will be a joint session with the other conference, and it will take place in the other building. So in the afternoon, you will not find anybody here, at least not speaking. So you should go to the others. But this morning, we are still here, and we will start with Darren Crowdy, who will tell us about low-Reynolds number swimming.
Okay. Can you hear me? Does that sound good?
Yes.
Okay, great. Well, thank you very much to the organising committee for inviting me. I will actually talk about low-Reynolds number swimmers, but that's a bit later. My talk's a bit of a hodgepodge, but there's a story behind it, and I thought I'd tell you the story of my interest over the last few years and kind of where my nose has taken me. So I'm a theoretical person, so I kind of, last 3 or 4 years I've been reading around the micro and nanofluidics literature, the colloid science literature, biofluid mechanics, low-Reynolds number swimming, and noticing that there's a lot of mathematical commonalities that seem to arise in these different areas that I guess there's the opportunity for technology transport, mathematical technology transport, and I guess that's something that interests me. I'm not an expert in any of those fields, by the way. That's my disclaimer. So I defer to all the other experts in the room, but I hope I can tell you at least something that you might find interesting. So, does anybody recognize what that's a picture of?
I think everybody.
Everybody. It is. I'm homing in here on a lotus leaf, and as you can see, the water there is beaded up on this leaf. It's kind of a lotus leaf effect. So the study of superhydrophobic surfaces is kind of a hot topic at the moment, and there's a lot of effort in trying to mimic the slip properties of these special surfaces, and in particular these superhydrophobic surfaces are characterized by having high contact angles and low hysteresis, and in particular if you look at this, I'm homing in even more here, you can see that the reason they have these special slip properties is because of this very clear microstructure here. In fact, kind of like pillars, if you like, these little pillars that the drops rest on. Generally, it's roughness of these surfaces that allow some interesting slip properties. The frictional properties are not perhaps what you might expect of a surface. And in particular, here's a droplet sitting on kind of a model of these surfaces. So these black regions here are just no-slip pillars. And the dark grey here is fluid. And the lighter grey are little pockets of trapped gas. Okay, and the people in the industry call this the Cassie state. So you've got these little pockets of, so surface tension kind of conspires with you to allow these trapped pockets of gas. And so if you imagine a shear flow over this surface, this isn't flowing over a wholly no-slip surface. Where it touches the black regions is indeed a no-slip surface, but then in between you've got these kind of spanning menisci. These are free surfaces between the liquid and the gas. And so really what you've got here is a zero shear stress surface. Actually, you've got a full capillary balance. Okay? And it's of great interest to try to... And by the way, let me introduce this now, because I'll talk about it a little bit. There's this protrusion angle look. So it's very common in this industry to assume kind of a Laplace-Young balance. So you've got a circular arc, really, or a spherical cap, and you're basically ignoring the normal surface stress balance, and you're just basically imposing a zero stress condition. And you can characterize these by the various protrusion angles of these menisci into the fluid. So please remember theta, that's going to be the protrusion angle. So in the Cassie state, look, this is another picture of what I'm going to focus on here, unidirectional surfaces. So here's where these little spanning menisci kind of are two-dimensional surfaces. I'm looking down on one here, and when you've got a flow over something like this, of course, you can either flow longitudinally along these pillars and menisci, or you can flow this way, over it in a transverse direction. And remember, these aren't no-slip surfaces, so in principle, at the level of the surface, the fluid is effectively slipping over this, and it's common to introduce a quantifier, which I'm going to call the effective slip length. And here's a little schematic of what I mean by that. So if you're actually on a no-slip surface and you've got a shear flow, then the actual surface is the no-slip plane. But here's a flow over some other kind of surface, and it's kind of an effective boundary condition here. So look at this. My effective no-slip plane kind of penetrates into the surface by some distance b, which I'm going to call the slip length. Okay? And the name of the game is to try to enhance the slip properties, increase the slip length so that the slip plane kind of goes into the surface. It's not where you'd expect it to be. And there's a lot of work in this. In microfluidics, of course, you've got small scales, you've got low velocities and very viscous fluids. So unless you try to enhance the frictional the slip properties of these things, high pressure gradients to force the flow through these things. So it's of great technological importance. Let's look at some mixed boundary value problems then, because these are mixed. When I say a mixed boundary value problem, I'm thinking of an elliptic field equation, normally at low-Reynolds number. And then on the boundaries, you may have one or more boundaries. On each boundary, you may have different types on contiguous portions. Okay, different boundary types on contiguous portions. So, for example, this is kind of a canonical problem in the field now. So I've got transverse flow. So these are I've got flat interfaces here. I'm focusing on theta's equal to 0. So these aren't kind of, these don't span like this with some non-zero protrusion angle. These are flat, no shear slots, and in between these are no slip surfaces. And I'm going to flow transversely across these. So these go into the board. Okay? And the question is, if you give me a particular no shear fraction, how much of the period window, it's periodic array, how much of the period window does this no shear slot occupy? You can ask, what's the slip length? And I put a little perp because it's it's kind of transverse to the slots. And this slip length here is clearly some fraction of this, some function, of this no shear fraction. But what is it? What is that fraction? And this, interestingly, is you've got a Stokes flow with mixed boundary conditions. Okay, so it's a mixed boundary value problem for Stokes flow. No slip here, no shear stress there. What if I flow the other way? So now these little dots, look, I'm flowing into the board, along the slots. This turns out to be an interesting mixed boundary value problem for Laplace's equation, if there's no pressure gradient forcing the flow, because what you really have is just the axial velocity along the slots, and it's just a function of x and y. And in fact, it's harmonic. So you've got del squared w 0, and then on here, you've basically got a Neumann condition. The normal derivative is 0. That's the no shear condition. And then W is 0 on here, no slip. Okay, so I've kind of got Dirichlet-Neumann boundary conditions. Periodic array of them.
Excuse me.
Yep.
Are these arranged periodically?
Yes. These periodically extend. Okay, so I'm thinking, let me just go back. I'm thinking about this, you see? So the dark regions here might be these slots. Well, this is now, funny enough, this paper was, Philip solved those two boundary value problems in 1972. I misquoted that, look, it's 72. This is a paper, funny enough, interestingly, this is a paper about porous media flows. And it was rediscovered 10 years ago by the super hydrophobic surface community, and suddenly now it's got a whole ton of citations, because the slip length that I was just telling you about, lambda perp, lambda along the slots, is basically, it turns out that the longitudinal slip length is twice the transverse one, and in fact the transverse one is given by log sec of the no shear fraction. So just remember that, log of the secant. And now this is a benchmark solution that everybody in the community knows. But as I said, interestingly, this guy wasn't talking about super hydrophobic surfaces, so it's a kind of canonical mixed boundary value problems. He happened to solve them. By the way, this is a remarkable paper. He solves a whole ton of other things as well, mixed boundary value problems. Certainly caught my attention. Well, let me just tell you something I did. I asked the question, suppose you've got a periodic array, but now you've got any number of flat slots in each period window. Any number, any size and shape. I was able to show that actually, first of all, the longitudinal slip length is still twice the transverse one, and this is the beautiful formula for the slip lengths you need. And omega here is a special function that I've been working on a lot over the years called the Schottky-Klein prime function that I know most people don't know about, but it's an extremely useful function, not least here. And it turns out, look, by the way, this prime function encodes the geometry of the slots in each period window. I've concealed a lot of parametric dependence of this thing, but it's still this very concise formula, and if you just let omega be this simple monomial, plug it into there, you get log sec, which is Phillips result. Okay? So now, however, with this formula, you can have as many slots in each period window as you like. And in particular, for example, I could put 2 in there. So remember 2 for the next few slides. Okay, so that was nice, because now, if you're talking about these unidirectional surfaces with 0 protrusion angle, we've pretty much nailed it, if we're looking at periodic arrays. But people observed a few years ago you can get negative slip lengths. Now think about what that means. If you've got y equals 0 is where you think your surface is, suddenly the effective slip plane has gone above the surface. Which means it's got more friction than a no-slip surface on the zero line. Okay? And people found these for super hydrophobic surfaces with these Cassie state surfaces. And what they find is that there's this interesting kind of competition between the little bubbles protruding into the shear flow. They might be able to slip along them, but if they protrude too far, you can actually negate the slip length. Okay, so there's a competition being able to slip over these things, but if you protrude too far, you disturb the flow too much in transverse state. And in fact, that critical protrusion angle, theta, is around 60 degrees, interestingly. So you can have a kind of protruding surface at 60 degrees, which is effectively a no-slip surface. So let me just tell you, so here you go, this I should have clicked, sorry. So when this is about 60 degrees, this protrudes and perturbs the flow too much, it disturbs the streamlines too much to get any advantage from the slippage over this. Okay? Some people call these bubble matrices. They're kind of, and here's how one looks like in 3D, so you're imagining now that you've got this non-zero curvature of the menisci. And as I said, I'll tell you why I got interested in this. It's because my PhD thesis was actually on free boundary problems in Stokes flows. Now, this isn't a free boundary problem only because you don't let it be. People don't want to solve the free boundary problem, so they just assume it's a Young-Laplace constant curvature. But in general, it won't be. It will be capillary number dependent. Okay? So these won't actually be circular arcs. You're going to have to solve for that as part of the solution, strictly speaking. So I was interested in that problem because I'll show you what's known about that, but not much. And in fact, there's disagreement. Let me just show you what I did first with this problem. It turns out Davis and Lauger in 2009 wrote a beautiful paper, just one of those four-page physics of fluids things, where they pointed out that you can find an explicit formula for the transverse slip length. Here it is. It's not quite explicit. You have to do integral, but the integral is explicit. You can see that they use Mellin transforms. You use S for Mellin transforms. So a clever piece of analysis here. And they actually showed, by the way, that around 60 degrees you do see this cutoff of the slip length. When I read that, I asked the authors, I said, well, what's the longitudinal slip length as a function of theta? They didn't know, and nobody did, so I actually found that, and it is completely explicit, this interesting function of theta here. So the nice thing is, by the way, this is in dilute, so these things are quite well spaced. We can't actually do the full problem, analytically at least. But at least in the dilute case, we have a fairly complete characterization of what they call the slip tensor. In other words, if you've got an arbitrary shear flow across this surface now, what are the components of the slip tensor?
Darren, what about the lambda perp lambda parallel relation?
There isn't. Here they are. Look how non-trivial. Look.
It's not 2 anymore.
No. Look how non-trivial it is now. Look. Remember, if theta is equal to 0 here, you get half ratio.
If they're well spaced over the capillary length, so then the gravity will come in.
Yeah, we're ignoring gravity.
And the entire thing will collapse.
Well, yeah, you're making assumptions about the pressures when you're doing the Young-Laplace balance here. But people assume that there's the normal stress is balanced, and then they just impose 0 stress to solve these boundary value problems. Okay. What am I doing next? Oh, Yeah, so all of that was zero capillary number. So surface tension is so strong, you can ignore everything else and it's a circular arc or a flat interface. But that's of course not real. And these people did some experiments and they find from these experiments, so I understand, I have to admit, because I'm not a physical scientist, I found this quite hard to read. But apparently, if you increase the shear rate, the effective slip increases. And these authors came along and did some Lattice-Boltzmann simulations and showed completely the opposite. And by the way, Spragalia and Prosperetti, I think that's how you pronounce that, they actually looked at the longitudinal flow problem, where they took Phillips' solution for flat, and they did a weakly curved analysis, perturbation analysis. Kind of interesting. Bit of a boring case. I think that there's more interesting things to do there, but that's pretty much the only piece of analysis that's been done as far as I'm aware. Any other questions? Okay, so I'm interested in what does the capillary number do? What happens if you allow this interface to deform and you let it equilibrate? How does the slip length depend on that? Of course, you're suddenly in a non-linear problem now. Well, I don't want to give any details because I haven't finished it yet. But I found the solutions. It turns out I've been able to find analytical solutions. I wasn't expecting that. I found analytical solutions for arbitrary capillary number. Okay, and of course you have to. It's a free it's a mixed free boundary problem now because I have to find these free capillary surfaces as part of the solution. I won't give you the details because I haven't finished it yet. But I will tell you where I got the inspiration from.
This is the periodic case without the added structure.
Say that again.
This is in the
periodic case and transverse flow, the difficult one, Stokes flow. Remember, transverse is Stokes, longitudinal is Laplace. I can't actually solve the Laplace one analytically. But the transverse flow, you're solving Stokes, free boundary formula for Stokes flow with these free capillary boundary conditions here, no slip on the thing. So you've mixed, but you solve, and it's periodic, yeah.
So, Garen, do people ever think about flow at an angle to the...
By linearity, at least if you're assuming the shape of the surface, you just superpose.
But not anymore.
Not anymore, no.
Is the protrusion angle, these surfaces are, the no-slip things are curved now, are they?
Yeah.
You're drawing that? Is the protrusion angle 0?
Very good question. I can find analytical solutions when they're free and curved, but protrusion angle 0, and I'll show you how I did it. Okay, so look at this. So as I say, I'm a mathematician, which means that I don't really know what an experiment is, but I can see the boundary value problem you're trying to solve. And I knew, because I know Mike Siegel very well, I knew about this work from 1999, which is absolutely fantastic. Full credit to him for this. Anybody recognize this? We ought to. We're in Cambridge. This is the bubble in Taylor's four-roller mill. So you imagine up here, here, and here, and here, four rollers producing a straining flow at the center of this apparatus, and you've got a little bubble there. And Mike Siegel was interested in thinking, lots of people have studied this course, but Mike was interested in seeing what he could do analytically, and he was, what you do is you put surfactants. He was interested in surfactant effects. Taylor didn't consider the effects of surfactant, well, he mentioned a few things, but didn't really think of it in those terms. And now you imagine that on your bubble you might have some impurities as surfactants. And here's the interesting thing. Mike assumed infinite Peclet number, so this surfactant doesn't diffuse off this interface. Okay, it just stays put on it. It just gets rearranged. And if the capillary number is high enough, in other words, if you're forcing this flow sufficiently long, well, first of all, if it's weak, if there's a weak flow, the whole thing's covered in surfactant. And then at infinite Peclet number in steady state, guess what the boundary condition is?
No slip.
Was that?
No slip.
No slip. So if you've got a fully covered bubble, you're no slip. That's the boundary. That's the problem you have to solve. If you increase the capillary number, if you increase this strain rate sufficiently, then it clears. What you produce is clean flow, clean regions. There's no surfactant here, but you have a full free capillary balance. And then all the surfactant gets pushed onto what they call these stagnant caps, and they call them stagnant precisely because in infinite Peclet number they become no-slip regions. Okay? Can people see what I saw? And by the way, he solved this mixed free boundary problem analytically using Riemann-Hilbert method, singular integral equation formulation. Nevertheless, those singular integrals were quite hard to compute, even though you knew them analytically. They had Cauchy kernels and square root singularities everywhere, but nevertheless, they were analytical. But you can see why I was interested in these, because look, this is free capillary surface, and then this is no slip. So you've pretty much taken one of these period windows and closed it up on itself, and then you've got a flow around it. It's the same mathematics. So I was interested, can you learn from this to produce flow over superhydrophobic surfaces with non-zero capillary number? And the answer is yes. But of course, I recognize pictures like this somewhere else in the literature. Oh, by the way, I rederived. I've managed to find. First thing I did, by the way, was rederive Siegel solutions, which I saw him last month. He agrees that it's a better way. There's nowhere near the mathematical complications to compute them now, and I use that prime function I mentioned. And notice, it's very important. Look, there's now 2 slots per period window. So I used the analysis I had done earlier, I closed it up, and I used the genus 1 prime function. I can say that here, it's Newton Institute. You close it up, you've got two slots per period window here. So now we've got a new representation of these, and I've generalized it to the surfaces. But look, these pictures reminded me of this kind of thing. Janus particles. And here you're deliberately inventing surfaces where you've got 2 different things going on in 2 different halves of the surface. So here are some colloids. I think, what are these? So these are catalytic and non-reactive. Here's some other architectures. I'm just showing you this to show you the kind of things that people do here. Apparently these are quite easy to make in the lab. And so, and they break symmetry if you put them in various fields or have them self-propelling. These little micromotors have interesting properties. And I know there's people in this room who know a lot more about this than I do. But as a mathematician, one of Ray's slides yesterday was called the games people play. Well, one of the games I play is I just invent my own Janus particles just to see if I can solve for them, find the locomotion speeds. And there's 2 mechanisms that I'm aware of. Well, there's lots, but these are the ones I'm going to focus on today. So chemical reaction. So you have these 2 faces of the Janus particle. On one, you've got chemical reaction, different on the two surfaces. And by the way, I have to thank the authors. I think at least maybe a couple of them are here, I think. So this was a great paper for me to learn about this, because they kind of cut it down to the essence. So I appreciated that. And then I actually invented my own Marangoni swimmer before I realized that people were actually doing this. I kind of found this by accident by reading somebody else's paper. So what I've been doing is I've kind of been inventing these things to see if I can solve for the locomotion speeds. Also, here's the paper that I was just saying. So look, here's a 2-phase Janus particle, and what you do is you kind of produce solute on one half, and then you suck it in on the other. So there's a solute gradient that produces a phoretic slip velocity in the other direction, and then you effectively end up going this way. Okay? So these are driven by their own kind of chemical reactions on the surface. And they're inventing different, geometrical scenarios here. By the way, these, number 1, are kind of the easy ones. I'll show you why. So here's my own. It's just a 2-dimensional one. I make no apology for that. And what I've got is, I'm going to solve for some solute concentration outside this thing. I'm assuming 0 Peclet number now. And I've got this Neumann-type condition with diffusivity and some surface activity here, which I'm going to take to be piecewise constant. Okay? And then you get this phoretic slip velocity, this tangential slip along the boundary using this rule. Okay? And m here is some other piecewise constant thing that takes different values on the 2 sides. Okay, so this is a Laplace type problem with mixed boundary conditions. And anybody know what kind of singularities the function will have here? Well, in 2 dimensions, you can think of these as analytic singularities. So you've got a complex potential involved here. It turns out, of course, you've got to have logarithmic type singularities, so it jumps. Things jump across these points. And you can resolve this analytically, it turns out. And then once you've solved that boundary value problem for C and you've got US, turns out that this is what the swimmer speed is, just this integral, which is quite nice. Some people say that it comes from the reciprocal theorem, but I don't believe that, because you can't use the reciprocal theorem here, because you can't solve the dragging problem. But it's nevertheless this. You can argue it a different way. So this is kind of easy, because once you've solved the solute problem, you've solved the Stokes flow part kind of easily. This is it. This is all you need to use. Okay. Anyway, you solved that, and this turns out to be the speed, where R is the coverage ratio. Okay, so it's kind of nice. You can produce these. And by the way, look, they're interesting nonlinear functions of the coverage ratio. And lambda here is just the ratio of mobilities. And it turns out that if lambda is between 0 and 1, the ratio of the mobilities is between 0 and 1, it's monotonic. But then you get these local maximum of the speed in particular directions.
Would that be minus 1?
What was that?
Or the minus 1 for lambda?
Which one?
The upper curve has lambda equals minus 1.
Yeah.
That's a ratio of mobility.
Oh, should it? You can't have an effective negative. All right, ignore that one. Yeah, okay, I don't know. I was just exploring. But you still see it for if you're above. If you're not, you see it's monotonic in here, and then you. Yeah, I guess these have to be positive. You disallow that. The type 2 is kind of more interesting because this goes back to these other problems I've just been talking about from superhydrophobic surfaces. Now you do not know. Even if first of all, I decided here to impose a tangential stress and then have a no slip. So I'm imagining that suppose you've got part of the interface that's producing a surfactant distribution, which is changing the local stress. If it gets swept to the back at high Peclet number, you'll get a no slip zone. So I was able to solve this too. Again, you have to actually get into the details of the Stokes flow problem here because you don't have that slip integral. You can't just integrate the slip law because you don't have the slip velocity. You have to solve for that as part of the solution. Okay, what I'm going to do now for the last 15 minutes is just to do the following thing. I've looked at these particles in free space and found their velocities. And by the way, by solving the problem analytically, you not only know the translation velocities, but you know all about the flow they generate. In particular, you know the entire multipole expansion. And what I'm going to do now is I was interested in what happens if you put these near a no-slip wall. Whichever one you pick. Pick one of these particles and put them near a wall. And I just want to show you briefly how I was able to make analytical progress here, even though you didn't expect to. So I don't need to remind you of the Stokes equations, incompressible Stokes equations. In 2 dimensions, you can introduce the stream function, which of course is related like this. Now, I think the next slide contains the thing that most people don't do, except I know a few people here do. Take the curl. You can show that the vorticity is harmonic. Vorticity is related to the stream function like this, and of course what it means is your stream function is biharmonic. Now, this is the general solution to a biharmonic equation in 2 dimensions. You introduce two complex potentials, F and G. And this is really underused in the low-Reynolds-number hydrodynamics community, but it's got lots of advantages. And if you want to know things like pressure and vorticity, you've got 2 functions, F and G. The derivative of F just tells you basically about forces, and then U and V come from this. So you give me any boundary value problem, I need to find F and G. It's an analytic function theory problem. And of course we're in Cambridge, so I should mention this. If you want to do modeling, of course, you think about making F and G singular in the flow to model what's going on there. One of the things you can do. The other thing is you mustn't forget that at any corners or contact lines or changes of type in the boundary conditions, these functions will be singular. And in fact, the famous examples is if you've got a corner, it turns out, sufficiently low angle, it turns out that this F and G have branch point singularities. Those are actually known as the Moffat singularities. Okay? But they're also going to have them at these, even at 0 contact angle. Because it changes type, you're still going to have singularities. And another reason why you really must, if you're doing 2-dimensional Stokes flow and you do free boundaries, you really shouldn't use these functions because look, you can integrate the stress condition. So first of all, you're not taking 2 derivatives to evaluate the curvature. That's one advantage right there. But notice this is very similar. This is the stress condition where that's the surface tension. This comes from the curvature. Look how similar it is to this. It's almost the same, except I've swapped the sign there. The velocity is given by this, but I've got this plus there. Okay? And if you want to introduce surfactants, you let the surface tension depend on the surfactant concentration. This is equation of state. Now, here's the crucial thing. If you change from no slip to a free capillary balance, this change of sign basically means that you get square root branch point singularities of F. Okay? So locally, around any point where you change type, you'll have a structure like this. Okay, so velocities are bounded, but stresses are, strictly speaking, unbounded there. Let me just show you this, because we're in the Math Institute. This is the idea I use to solve these. Is Mike Graham here?
Yep.
I'm going to do this little thing again that I did it in New Jersey, and see if anybody knows the answer this time. Does anybody know how to do that integral?
Log plus 10.
What's that?
Log plus 10.
Yeah. How do you know? You just remembered? You've taught it.
Had for a long time.
You've taught it. Yeah.
Yeah.
Do you now? Okay. So what about this one? Oh no.
T is tan theta over 2.
Aha! Mike, we're successful this time. I did this. I asked the same question in New Jersey, and it was complete silence. It was like, I guess they.
One thing I remember from New Jersey.
Yeah.
Say it over.
Yeah. Right. You see, Mike made a note of it. Do you teach that?
Yeah.
Yeah.
The Oxford undergraduates will be able to answer that.
What was that?
All the Oxford undergraduates will be able to answer that.
Okay.
I've got my hands on them.
Yeah. Well done. Well done. Well, you know what? Next time you can tell them that if they know this, you can get insights into solving for superhydrophobic surfaces. So look, do you know why this? Do you know why? By the way, this is an interesting question. This is what this slide is all about. Do you recognise anything on this slide from your lectures?
Yeah, there's things at the bottom.
Those things at the bottom. That's why I've called it T, because some people called it for the T substitution. Do you know? So you might. This is kind of interesting. Look, look at this. This is an algebraic curve, circle. Now, does anybody? I'm going to just tell you a little bit about uniformization. If you've got a curve like this, look. If you want to know y is a function of x or a point on the curve, you can do this. Look, you can. But look at this. I hate this. I hate that because you have to choose depending on which part of the curve you're on. Right? Now, can anybody see another way, a more convenient way to do this? Well, I know that if x is cos theta, say, and y is sine theta, then x squared plus y squared is identically 0. And that's why I'm thinking about integrals like this, because here I am. I'm sitting on this curve, basically. But look at this. I don't need to use cos and theta, cos and sine. I can use these. This is another uniformization of this curve. Theta is one uniformization, cos and sine. X is cos theta sine. This is another one. Quickly do it in your head. We can all do this. Square that, add square of that. You'll see everything beautifully cancels out to 1. It's the T substitution. And what you're doing is you're providing, instead of the cos, sine, kind of, those are transcendental functions, you're using a rational function uniformization of these curves. And you don't see any square roots. I'm using exactly the same idea here, because what I'm going to introduce, look, is this beautiful slip map. And what it does is I'm going to do all my analysis in the upper half plane. So this is kind of like my T-plane. And I'm going to push it forward by this map. By the way, omega is that Schottky-Klein prime function I keep telling you about. In fact, in this case, it's just this, like it was for Phillips solution. And it maps this upper half disk to the exterior of this Janus particle. And look what happens is, look, as you go around this corner, you open up the angle to this. So that's why the inverse has got these square root branch points. So what this means is, remember, my f of z had to have square root branch points. But if I think of it instead as a pullback function of f of zeta, it's going to be analytic as a function of zeta. So the branch points will be there, but I won't see them. It's a bit like doing the T substitution. Anyway, that's the secret of my success. You can do that in all of these problems, and it's why I've been able to find these new solutions. You uniformize the surface. Okay? So these are the two. This is just to show you the free space speeds. I've got 10 minutes now. Okay, I'm just going to be able to rush through this. As I said, I'm going to put these things near a no-slip wall. Let me just show you a little story. What's known about swimmers near walls? One thing people know is that low-Reynolds number swimmers are attracted to surfaces. I learned this 4 years ago, 2009, but not least from reading this paper. And these people measured, they repeated an old experiment where they put some bull sperm between two plates and then measured, let them go, and then measured later on what the distribution of the sperm across the plates was. And this is across these two plates, and look, you can see they clearly aggregate at the walls. Fairly symmetrically, because they just kind of go to the closest one. Those authors decided to put forward the following explanation for this. They said that they can't help but do that because there's a hydrodynamic reason for it. So swimmers are normally approximated by stresslets, which are like force dipoles. So you've got force plus force minus force. And these authors looked at what happens to a stresslet near a wall. And the nice thing about this is you can use a method of images here, and they argued that if you're a stresslet that's aligned with the wall, you will be attracted to it. So the argument then goes, if you're a stresslet that isn't aligned with the wall, this is the angular velocity that you'll experience, and therefore you will always tend to get aligned with the wall, and hence attracted to it. Okay? So if you're an arbitrary oriented stresslet, there's a mechanism by which you will kind of straighten out and move towards the wall. Level out and move towards the wall. But at the same time, this is when I came into the story, because I watched Yizar Orr give a talk at UCSD, it was, on these things. He was inventing these little well, they're not micro swimmers at all. They're macro swimmers. These are little spheres attached with rods. He was building these little networks of spheres and rods and actuating them by having these rotate at some angular velocity, coming out of the axis, coming out of the ball. And and what he did was, I haven't got much time, so I'll rush through this. He used this work. I see John Brady sitting there. You can actually find the mobility tensors, they're called, that relate the forces and torques to the velocities and angular velocities for a sphere near a wall, which is precisely what Orr and Murray had. And this is typically one of the entries of this stress of the mobility matrix. I just picked one, I guess, just to show you kind of what an impressive exercise it was to code all this up and then do all these numerical experiments. Let me show you what they did. They found it. This is what they called a 2+1 swimmer. So this is like a sequence of what they observed. They found that it basically equilibrated to a steadily translating state moving along the wall. Okay, these are full numerical simulations based on those mobility tensors, and here are some phase portraits. So this is how the angle changes, the orientation of the swimmer changes as it settles down, and then the height against the orientation settles down to this kind of spiral point, or what's it called again? Anyway, that point. That was one of the things they found. They also found these nonlinear orbits. So what happens is, this is a two-sphere swimmer. You can move away from the wall, but then you kind of reorient and then start moving back again. You reorient. Look at it reorienting here. It's quite a dramatic, you can see it, dramatic reorientation. And then you engage in these periodic orbits. Okay? So you don't just get attracted to the wall necessarily. You can actually move away from the wall. And here, so for example, if you look at this orbit here is basically one of these. This is height against orientation, and that steadily translating state is the little center there. Okay, so that's just moving without going up or down.
So are these at different values of some parameter?
Initial conditions.
Uh-huh.
Yeah, so plus they are actuating, they choose different angular velocities to change the actuation mechanism. And then these are the kind of things they see. Here's a three-sphere swimmer. Anyway, you can see the picture, and they actually these are sponges keeping two cylinders afloat in a tank of viscous fluid, and then they turned these on and actually tried to do an experiment. And here's the picture. They kind of see these kind of bouncing orbits. And this is the thing that really. Let me remind you about this one. This is the steadily translating orbits. I learned about this from watching the talk, but then I also read a paper on sperm from the Birmingham group, these people, and these are completely different simulations. These are numerical simulations together. They use a Chang-Wu solution for the head and then some slender body thing for the... And they do these simulations, and look what they find. They find exactly the same kind of settling down to a steadily translating orbit. So I was intrigued. You don't necessarily crash into the wall. Sometimes you have a nonlinear orbit. Sometimes you settle down to a steady state. And I wanted to understand what was going on. And by the way, you see this in all these different swimmers. Elliptical heads and so I wanted to understand. And so what I did was I invented my own swimmer. It's not the Janus particles yet, but you'll see I'm just going to replace it with the Janus particle later. Let me just show you what I did. So I took a circular cylinder near a wall, and I decided, let me impose a slip velocity. I'm just going to pick it to be whatever I like. There's lots of experts here. Does anybody know why I picked this one? We actually saw this yesterday in Stark's talk. I've got sine of 2 times basically the angle. He had sine of the angle plus something, beta I think he called it, times sine 2 of the angle. And then the sine of beta determines whether it's a pusher or puller.
Which reverses velocity midway across theta equals pi.
Yeah, but notice I haven't got any sine theta. I've dropped sine theta, so I've got I know that I'm going to get a pure stress with no dipole term, so these won't be self-propelling. And do you know why I did that? I thought, well, if I'm going to investigate wall effects, I want a non-self-propelling swimmer first to see if that can move because of the interaction with the wall. Okay. All right. And now this is where I can wrap this up. So here's what I did to cut a long story short. I picked that swimmer because I knew about this beautiful solution from 1981 by Geoffrey Yonanishi, which is the analytical solution to this problem. This one. There's an analytical solution to the dragging problem of a cylinder near a wall. And they solved it using bipolar coordinates. So I'm going to use the reciprocal theorem. I'm going to use the exact solution for the dragging problem, and then here's my problem that I need to solve, and I won't even have to solve for the flow field around my swimmer. I'll get the velocities I need from the reciprocal theorem. Let me just tell you, so this is what the reciprocal theorem tells you for swimmers. So this is a force and torque in a dragging problem in the same geometry. These are the things I'm after. This is my imposed tangential velocity, and this is the stress tensor from the dragging problem, which I know. So the dynamics here reduces to calculation of some integrals, and so first thing I did, by the way, was to rederive. I solved Geoffrey Yonanishi's problem in here because it's much easier, and you end up with rational function integrals again. And there it is. And look at this. I'm so proud of this because it's so simple. You can do all the integrals analytically, and you end up with this beautiful nonlinear dynamical system for my circular swimmer with the sine 2 theta imposed. Absolutely beautiful. There's no approximations here either. This is the exact solution, and of course it's integrable. And in fact, these are the curves. And I bet you're all dying to see what they look like. Look at that. Look at that. I didn't need all those tensors and anything. Basically, I didn't need anything. I just posed the problem, and now my circular swimmer seems to have qualitatively similar dynamics as the sperm and these rod sphere combinations. And you can see these little centers are the steadily translating states, and these are these nonlinear bouncing orbits that you see. Does anybody notice a difference to the one I showed earlier?
There are no tumbling states.
Let me just. Here we go. Who said that?
No tumbling states.
Yeah, look at this region. I don't have that. Does anybody know why? These are ones where you escape. And I don't have those because mine's not self-propelling. So it's always trapped near the wall. If I added a sine theta contribution, like we saw yesterday, you get one that looks exactly like this. You can now escape if you're directed away from the wall. Okay? But anyway, I'll finish now. But basically, you can use exactly the same mathematical technology, the reciprocal theorem with the Geoffrey Yonanishi solution, to put these Janus swimmers near the wall, and we've done all of that too. And I don't have time to tell you about it. But thank you anyway.
We had already many questions by the speaker, maybe we have somebody already.
You do have a state where the theta increases indefinitely, but does the distance go to zero?
Yeah. No, the distance goes up. It goes away from the wall.
Can we bring that?
Oh yeah. Yeah. If Oh, you're talking about my solution.
No. This is what I meant by the tumbling solution. So you have between your right. So there are trajectories that are bounded, but do they touch h equals 0 at 90 degrees? And
No. They get close and then they reorient.
So they tumble.
Oh, okay.
If you think about a sperm cell, then often they form helical paths.
Yeah.
So you cannot do
No, we can't do those.
problem.
Not using this, no. But the sperm simulations I showed you, they have in-plane beating, but then they do look very similar to this.
Do you see any other questions? So let's thank Gary again.